mouse might.
So it's in my chair?
Hello. Please take your seats. We are going to start the morning session of the second part of ICHEP. So we want to start on time. Okay, so let me start. So good morning to everyone. On behalf of the local organizing committee, it is my pleasure to welcome you to the 43rd edition of the International Conference in High Energy Physics. My name is Rogério Rosenfeld, and together with Inácio Bediaga, we co-chair the local organizing committee of this conference. As you know, this is the first time that ICHEP is hosted in Latin America. This meeting is a unique opportunity to showcase the work in high energy, cosmology, and astroparticle physics that is done in our region, in Latin America, where a large community has developed in recent years. This is demonstrated by the associate membership of Brazil in 2024 and Chile this year in CERN, and also Brazilian scientists participate in all 4 major LHC detectors. Furthermore, there is an active participation of scientists in the region in cutting-edge experiments in neutrino physics, such as DUNE and CONI, in cosmology, such as the Legacy Survey of Space and Time in Chile, that is based at the Vera Rubin Observatory in Chile, and in astroparticle physics, such as the Pierre Roger Observatory, which is hosted in Argentina, and the Cherenkov Telescope Array, also in Chile. We are very pleased to receive more than 900 physicists from 54 countries for a week of intense discussions and exchanges here in Brazil. It is an incredible sight to see this auditorium filled with people. So we are making history. The official opening ceremony will take place later on with the participation of the Minister of Science and Technology of Brazil, the Governor of the state of Rio Grande do Norte, where Natal is the capital, and several other important authorities. We thank you all for coming and wish you a very productive meeting. Thank you.
So, good morning. Welcome to the ICHEP plenary sessions. And it's my great pleasure to announce our first speaker for today. It's Kerstin Techman. And Kerstin will talk about the latest results from the ATLAS experiment. Kerstin? Thank you. Thank you. The floor is yours, Kerstin.
So it's really my pleasure and my honor to show you the highlights from the ATLAS experiment. And over the past decades, the standard model has really been extremely successful in describing collider-based measurements over many, many orders of magnitude. And one of the goals of the ATLAS experiment has been to probe the standard model broadly and deeply across all its sectors. You see a summary here of cross-section measurements from the most abundant soft QCD processes that are happening at the Large Hadron Collider to very, very rare electroweak production of, for example, dye boson events. And there's still many open questions that we have nowadays. What is the dark matter that we see in the universe? What is the origin of the matter-antimatter asymmetry? Why do we have 3 fermion generations? How do we explain the big gap between the electroweak scale and the scale of gravity? What is the nature of the electroweak phase transition in the early universe? And in addition to probing all the sectors of the standard model, another thing we're doing is to search directly for new particles, for new phenomena. To give you just a small glimpse of the breadth of the models and of the signatures that we probe, here's a plot that summarizes our searches for new potential heavy particles, which we constrain, for example, by putting limits on what their masses could be in these models. The ATLAS experiment is one of the general purpose detectors that's operating at the Large Hadron Collider. We have excellent reconstruction, identification, resolution for our main physics objects, the leptons, photons, taus, hadronic jets. We also have excellent flavor tagging capabilities. So just as an example, our resolution for energy momenta range from the sub-per-mil level for some objects to the percent level for some of the others, also depending on the energy scale. For the most recent run of the Large Hadron Collider, Run 3, which just finished a little bit earlier this summer, we made some upgrades to our detector, for example, adding new small muon wheels here to bring down the trake rates at the trigger level. And we upgraded our calorimeter electronics to have higher granularity. And these were really driven to deal with the more harsh experimental conditions that we had in Run 3. So I just said Run 3 finished earlier this summer. We had been running from 22 to 26. And in this time, we collected 332 inverse femtobarn of proton-proton collision data at a center of mass energy of 13.6 TeV. We were running with a pileup, so this means the number of proton-proton interactions we're getting in one bunch crossing of about 64. And this is more than 3 times of what ATLAS was originally designed to run at. Nevertheless, we have high recording and good for physics efficiencies of 94% and above. And this data set, in comparison to our Run 2 data set, increases our total PP data set at the 13.613 TeV-ish range by more than a factor of 2. In addition to this, we also collected a diverse set of heavy ion collision data. So we multiplied our lead-lead collision data set by more than a factor of 4. But for the first time, we also took collision data for light ions, so oxygen-oxygen and neon-neon collisions. In our proton-proton collision data set, we also included a 1.26 inverse femtobarn of low pileup data. So this is running with a pileup of about 3 for precision measurements, like W mass measurements. And these event displays here give you a sense for how much cleaner this low pileup data looks in comparison to our standard PP data from Run 3. And the Run 3 data really holds many promises. What you see here are efficiency measurements, efficiency for reconstructing and identifying muons in our latest 3 years of data taking 24 to 26. And you can see here, as a function of pseudo-rapidity and phi, excellent efficiency and also excellent stability over the years. We also have much improved performance for our flavor tagging and tau identification methods for future analyses based on transformer architectures. So to show you 2 examples, this compares our current algorithm, GN2 in blue, our new one, GN3 in red. You see, as a function of the B-jet efficiency, how much our rejection for C-jets and for light jets improves. For the taus here, comparing the transformer-based in solid with the previous ID in dashed, you see also much better rejection as the function of the PT of the tau candidate. These new algorithms are not yet used in the analyses I'm showing you, but we will have them available for future analyses. So we are very much looking forward to continue exploiting this large Run 3 data set The analyses I'm showing you will include data up to 24 in some of the cases. So I said we are testing the standard model really broadly. Let's look first at some tests of the electroweak sector. And what we're doing here, among other things, is to characterize the Higgs boson in detail. What I'm showing you here is the most detailed, most precise measurements of Higgs production, that decays, couplings that we obtain by combining 26 individual analyses of single Higgs boson measurements and di-Higgs searches. So just some examples. In these analyses, we constrain the couplings to the heavy gauge bosons, the third generation fermions, to 5 to 12%. You see here the coupling modifiers, that's the couplings we measured, normalized to their standard model values. They're all quite compatible with the standard model. And they're actually much improved compared to our previous such analysis that we published 4 years ago. You can see comparison between the previous and the current analysis here, improved by up to 45%, thanks to improved input measurements that we're using here. We now constrain the charm coupling to be smaller than 4.1 in standard model value. We constrain the branching fraction of Higgs going to invisible particles to 12%. That's quite sensitive test of beyond the standard model physics. We also have constraints on the Higgs self-coupling, including both the di-Higgs searches and the single Higgs measurements, where the Higgs self-coupling enters through electroweak corrections. And these single Higgs analyses in particular serve to constrain, to lift degeneracies in the non-standard model part of the phase space. So measuring the Higgs self-coupling, testing the shape of the Higgs potential is really crucial to understand the nature of the electroweak phase transition in the early universe and the stability of the electroweak vacuum. So what I'm showing you here is a new analysis that we have for di-Higgs production using the BB tau-tau final state. We use transformers to separate the events into different categories and to split our signal from the background. You see one of the distributions of the transformer outputs here, and the signal is this red part that you see here. So it's quite small on the top of a large background. We do a joint analysis of the run 2 data and the 22-23 data from run 3, and we measure the signal strength to be 2.6 times the standard model expectation. You can see here that this is quite stable across event categories and runs. We quantify the significance of the signal to be 2.6 sigma, when from the standard model we would expect 1.2. And this single analysis reaches a sensitivity that's close to the Atlas plus CMS combination already. We have very good validation channels here with ZZ and ZH productions, which are both, in both cases, the signal strength we measure is close to the standard model value. And this is really our most sensitive di-Higgs search, thanks to not only adding the run 3 data, but also using improved flavor tagging, the GN2 algorithm I showed you before compared to the previous analysis, and improving our classification strategy based on transformers. Another subject very closely linked to electroweak symmetry breaking is the longitudinal polarization of gauge bosons. We have 2 new analyses here. The Goldstone equivalence theorem tells us that at high energy scales, the longitudinal polarization and the gauge bosons become equivalent to each other. In this analysis, we study inclusive ZZ production. We use a BDT to try to split the longitudinal component in red from the others in green and yellow. We measure the inclusive polarization fraction here to be about 8%. And for the first time, we measure this in different bins of invariant mass of the 4 leptons from the 2 Zs to become sensitive to the energy scale of the process. When we combine this with our run 2 analysis, we reach the first observation of production of 2 longitudinally polarized Z bosons. In the other analysis, we study vector boson scattering, which is really even more closely related to the mechanism of electroweak symmetry breaking. Here, we radiate 2 vector bosons from the incoming quarks, and they scatter off each other. We typically have 2 forward jets in the detectors. We again classify our events, and what you see here in this lighter sort of purple are the events where the Z boson is longitudinally polarized. You see these showing up nicely here. And in the joint analysis of run 2, using data up to 24 from run 3, we see first evidence for these events with the longitudinal polarization of the Z boson. So you see that these are still at the level we are reaching first significance for observation for evidence. So with larger data sets, these measurements will remain particularly important and will really improve with the larger data sets. So let me switch gears a little bit and show you one of our examples of a search for direct signs of beyond the standard model physics. And this is a search for dilepton resonances. In many of the models beyond the standard model, they predict appearance of new high mass vector bosons. We search here in dilepton final states, 2 electrons, 2 muons. You see here the invariant mass distribution of dielectron pairs. You can see how we model the background and how a signal of about 5 TeV would show up in this. And since we're looking at these very high energy scales, we profit in particular from the larger center of mass energies of run 3. In neither the dielectron nor dimuon channel, we find any globally significant deviation from the background-only hypothesis. So we go ahead and put limits, in this case, on a sequential standard model and on a E6 motivated grand unification model. You can see examples here, the new results in blue, the previous ones from run 2 in black, and their combination in red. And overall, compared to the previous result, our cross-section limits on a Z prime in a sequential standard model, where the Z prime would have the same couplings as the standard model Z boson, improve the cross-section limits by more than 60%, and the mass limits on this Z prime by 0.4 TeV. So after having had a look at the electroweak sector, let's now take a look at a few examples from the strong sector of the standard model. What you see here is the predicted mass spectrum for B sub C mesons, and these excited 2s and 1p states have been seen previously at the LHC, but this lowest excited state, the B sub C star, is expected to be very challenging to see because the mass splitting is predicted to be very small, just about 50 to 70 MeV. So the signature here is a decay, a radiative decay with a very soft photon. We reconstruct the B sub C in decays to J psi and muon, with the J psi itself decaying to 2 muons. And this photon here, the soft photon, is reconstructed when it converts in the material to E plus E minus pairs. And for this, we lower our tracking thresholds to just 100 MeV to be able to see these very soft photons efficiently. What you see here is a difference in the invariant mass between the J psi, the muon, and the photon with respect to the J psi and the muon. You see a very nice peak showing up here. We quantify this to be more than 8 sigma significant. The mass difference we measure between the B sub C star and the B sub C is compatible with predictions. However, it is a bit higher than what is predicted by the most recent lattice calculations. And this really constitutes the first observation of this B sub C star state. So another example from the strong interactions in very high temperatures and very high pressures, quarks and gluons are forming quark-gluon plasma. This is a deconfined state of the quarks and gluons. And this has been established to be produced in heavy ion collisions. A very direct probe of this is that partons that traverse the medium lose energy. So when we look at dijet events, when they're produced here at the formation of the quark-gluon plasma, they have different path lengths that they travel in the medium. And due to the energy loss, this leads to a momentum imbalance in these dijet pairs. And this was first seen in lead-lead collisions in 2010. And the question here was, what about lighter ions? Do we see this also in smaller, lighter ions, or do we not see this? And we studied this looking at the light ion data that we collected just last summer. Here you see for the oxygen-oxygen data, this plot shows you the momentum imbalance between the two jets. The black markers here show this momentum imbalance measured for the very central collisions where the two ions overlap almost completely. And then we go from, in the different colors, to less and less overlap, and we also compare two PP collisions, here shown in brown. We do the same here in the neon-neon data. And when you look at this plot, what you can see is a systematic increasing modification as we go to the more central collisions. And we quantify this to be statistically significant for the more central collisions, both in oxygen-oxygen and in neon-neon collisions. So what I'm showing you here constitutes very clearly an observation of parton energy loss, also in these light ion collision systems, where this had not been seen before. We do have a range of other new measurements that we're presenting here. I won't be able to go into detail, but just to give you a few more examples very briefly. We have a first measurement of the CKM matrix element VCB in TT bar decays, where one of the W's from the top decays into CB quark pair. You can appreciate here how small the signal is, the red here on top of the backgrounds, in this classifier output using neural networks. So at present, the precision here is not competitive with measurements that are obtained in hadron decays, but we have some very clear path ahead to improve this measurement, to be seen which precision we will be able to reach, but it should be better than what I'm showing you here. We also have a new search for a rare Higgs boson decay, Higgs decaying to LL gamma with a small invariant mass of the two leptons, smaller than 30 GeV, and a photon, with the data up to 24 from run 3. And combined with run 2, we reach evidence for this rare Higgs boson decay, the level of 3.4 sigma. We also have a new search for beyond the standard model decays of the Higgs boson, Higgs decaying to gamma and a dark photon, which doesn't leave any signature in our detector, with 23, 24 data. And for this analysis, we put in place a new trigger in these years that allowed us to target the most abundant of the Higgs boson production processes, gluon fusion. You see here the limits we had obtained in run 2, our run 3 result, and when we combine the two, we limit this cross-section to be smaller than 0.9% when combined. So after showing you our highlights from our current data, or some of our highlights at least, let's take a look towards the future. LHC is currently being upgraded, as well as the detectors, towards high luminosity LHC, scheduled to start in about 4 years from now. And with the high luminosity LHC, we aim to increase our data set to around 3,000 inverse femtobarn. That's about a 6-fold increase over our current data set. We will be looking at pileup of about 140 to 200. So just as a reminder, in run 3, we were around 60. You can appreciate in this event display of a simulated TT bar event how busy our detector will look, how busy these events are. We are currently upgrading our detectors to cope with these high occupancies and the harsh radiation that they will experience. So a few highlights of our upgrade program. We will completely replace our tracking detector by a new silicon tractor made of pixels and strips with about 50 times the number of channels of what we have nowadays in our tracker. We will also increase the coverage and pseudo-rapidity from currently 2.5 to 4. In the forward region, we will install a high granularity timing detector with a per track resolution of about 30 to 50 picosecond, which will help us to reject pileup tracks, so tracks from pileup events. We will have a new trigger and readout system where the first level trigger will operate at 1 megahertz. And for the first time, it will have available the complete event information from the colorimeters at full granularity, in addition to also having available high-resolution input from the muon triggers. So for the first time, this will allow us to have a global trigger that also takes into account higher-level features. To make this possible, we are upgrading our colorimeter and muon spectrometer electronics. Furthermore, we will improve our muon coverage. So we will replace the innermost layer of our barrel with including new resistive plate chambers to improve the trigger efficiency and reduce the fakes. To just give you a few highlights of our upgrade projects, Our silicon pixel module production is ramping up. We have about 1/3 of the pixels modules completed, and we are currently doing large-scale system tests on these. The silicon strip module production is also ramping up. We have about 1/4 of our long strip modules assembled, and we are hoping to start, or we are planning to start the loading of the structures into the support structures very soon. So here you see a petal loaded with silicon modules being inserted as a test into the structure that holds the end caps. Our timing detector sensor production is ongoing. We've had successful pre-production of modules at all assembly sites. And this is a picture of our global common module for our global trigger, the final prototype, which has been tested. So across all these systems we're in production, we've had several technical challenges along the way, which we have been addressing. So let me just conclude very briefly. I showed you highlights from Atlas across the different sectors that we are probing. The standard model searches for new physics. I give you some examples here. I won't read them out. You will find more results and also more details in the talks that will be coming over the next days, and also in the parallel session talks that took place last week. Furthermore, we are making good progress on our detector upgrade, and I hope I was able to show you that we are building a much better detector that we will have to use for high luminosity LHC. Thank you.
So thank you very much, Kerstin, for this wonderful talk on these very exciting results. And we open now for questions. We have one question here.
Well, thank you very much for your very detailed and complete review on the present status and future of Atlas. Well, for many years before the discovery of Higgs boson, this particle was a primary overarching goal of the experiment. And my question is, whether this primary goal for the future of Atlas experiment exists now?
So it's really multifold. It's multifold. I don't think there's one outstanding primary goal. Certainly di-Higgs production will be extremely interesting to be studied with a larger data set. At the moment, you saw the significance we have is about a good sigma. When we combine the different new analyses, probably a little bit more. So certainly here we need to keep working on this. I showed you the example of the di-boson longitudinal polarization studies, where also we're at the level of reaching first observation, first evidence, but really larger data sets will help us to look into these sectors into much, much more detail. So these are two examples I would give, but really there's also more to be explored in many other areas.
Thank you. We have time for one more quick question.
Please. So thank you for the nice talk. I'm wondering if you can enlighten us with your limits for monopole searches that I know you have.
I'm afraid I can't quote the number from the top of my head. We had a recent monopole search in heavy ion collision data in lead-lead from about 2 years ago, give or take. I can pick it out and let you know.
Okay, maybe we can take one more question. Yep, here.
Thank you, Kirsten, for the nice presentation. So on your slide 9, you present is that coming back to the di-Higgs, you had 2 results for the H8 and 8Z, and they both have different, one go down and go upwards. I'm wondering if they are somehow anti-correlated, if you could expect this kind of, if you one go down, the other one will go up.
I think in principle, yes. So what we're doing to obtain these measurements is effectively to change the target that we're looking at in the classification. So it's the same data set that we are probing for the HH, the ZH, and the ZZ. They're sitting fairly close to each other. So yes, I think this is not unexpected.
Thank you.
Okay, thank you. Let's thank our speaker again. Thank you, Kirsten. So continuing on our experimental results, it's a great pleasure also to have this morning Andreas Meyer from the CMS experiment, and he will bring us the latest highlights from CMS.
Yes, okay.
Andreas, welcome. The floor is yours. Thank you.
Thank you. Can you hear me? Yeah, okay. Thank you. So it's my distinct honor to give the presentation of the CMS highlights at this ICHEP. In fact, this is a historic moment because we have just finished run 3. We have the first results out, and run 3 has really been a game changer. Thanks to the amazing performance of LHC, we have recorded as much as 0.5 inverse autobahns in total, about half of it in the last 2 years since the last ICHEP. You see these very large, you see these very large data sets recorded in 24, 25. And of course, this gives us a huge amount of new data to analyze, some of which we have already analyzed, and I'm going to show some highlights. And then we are going to LHC, high Lumi LHC, where the detectors and conditions will be a complete new paradigm with 5 times more luminosity and much more powerful detector and trigger. So the run 3 data sets, as Kerstin already showed, there's a variety of data that we recorded, not just proton-proton and lead-lead, but also, for example, in 26, a large low pileup run. We took the data usually at very high quality, so the certification rates are about 95%. And we actually looked at the low pileup data already. They are, of course, taken in view of the improvement of the W mass measurement, but also for other purposes. And you can see here the first glimpse at the MT-L missing PT spectrum, taking Z events where one muon is removed, and the comparison between the data and the Monte Carlo simulation is excellent. So this shows really how excellent a data set we recorded in April this year. We also looked at diffractive events. This is the fraction of high mass jet final states in events where a proton is detected in the forward proton spectrometer. And you see that we can still see diffractive events even at mass levels of 1 TeV or more. So CMS physics is really the full 360 of the LHC. Of course, we cover standard model, precision, QCD, electroweak top, and Higgs, and also searches at the energy and luminosity frontier. But CMS is also a flavor factory, as I'm going to demonstrate, and also a heavy ion experiment. And we have actually extended on the frontiers that we are addressing in the last, during run 3. And so we've extended in particular in the area of trigger, where we are now able to also look at long lifetimes, lower masses, and we've invested in anomaly detection and other state-of-the-art methods of data analysis and data triggering. So HLT scouting is the trigger level analysis, where the concept is basically do more with less, do more physics with smaller data. The HLT is the higher level trigger, which is the hybrid system of GPU and CPU, where we reconstruct and select the events. We ran in 26 with 110 kilohertz input rate and 40 kilohertz output, of which about 30 kilohertz was scouting, which is just 15 kilobytes per event. It contains the higher level trigger objects, and it allows us actually to take much more data. In total, we've taken 600 billion events of scouting data in run 3. And you see here one example for the low mass dark photon production, which would decay into two fermions, two fermion pairs actually, two of which are muons. Muons we trigger and we put this then into the scouting, And you see that with even less luminosity than we had in run 2, we can actually improve the limits by a factor, especially in the low mass regime. We go a step further, and actually we are also doing level 1 scouting, which is triggerless recording entirely. So all bunch crossings in all orbits are read out, but only the level 1 information. There's a demonstrator system that was put in place in 24, and we actually were able to take first physics results in the search for heavy stable charged particles, which would move very slowly through the detector, covering several bunch crossings, and as a result are invisible to the conventional readout system, where minimal velocity is required to have all the data in the same time slice that can then be reconstructed. So you see here in the middle plot that the standard HLT efficiency actually goes up only at a velocity of beta of about 0.6 or so, and below we have efficiency only through this mechanism, and we are able to set limits as low as a few femtobarns for beta 0.2, so 20% of the velocity of light. Machine learning is, of course, a key at the trigger level. We have improved in flavor tagging, and substantial gains have been achieved not only before run 3, but also during run 3. You see here the efficiency for the Dihiggs to 4B trigger, which went up from 45% signal efficiency, from 18% signal efficiency to 45 on the left. And we also, in 24, deployed an anomaly detection system in the hardware using sub-microsecond autoencoders, and later in 26 also deployed a topological trigger, which actually complement the existing triggers, in this case here with high HT, or the inclusive muon triggers, where we invest a lot of rate in order to get to efficiency, while these topological triggers are able to select events that would otherwise not be selected. So the stairway of discovery is this. Kerstin showed the equivalent plot from Atlas. Of course, over these 14 orders of magnitude between the soft production of final states and the rate of where we assume new physics must appear, we are measuring, we are making precision measurements, and we start to observe. As I said, this is really a historic moment in time, because we have a complete run 2 legacy, demonstrated also by this figure, and we have the run 3 data in store now. We will have, I'll show that we have also the first run 3 results available, and actually full run 3 results for a few cases. So just as a demonstration, this is actually the range at which we are looking when we measure W boson properties. As you may know, short time after the last ICHEP, we made the best measurement, most precise measurement at the LHC of the W mass using the PT lepton spectrum. You see this on the right with an uncertainty of the order of 10 to the minus 4. Now, using the full run 2 and run 3 data set, 2016 to 26, we have 446 inverse femtobarns, and we are looking actually for decays of the W into 3 hadrons, for which the branching ratio is expected to be of the order of 10 to the minus 7. And if there was a signal, one would see it here, of course, at the W mass. So in the absence of a signal, we set limits of 2.4 times 10 to the minus 7. So this is the range that we're looking at, 10 to the minus 4 in precision to 10 to the minus 7 for branching ratios in the case of the W. We make precision measurements, of course, for QCD calculations, and also as input to improvement of calculations such as parton density distributions. Here's a measurement of 250 data points of Z plus jets cross-sections where the data are unfolded as a function of the PT of the Z and the relative orientation of the two jets. The bulk data in this case have an uncertainty of order 1.5%, and this is made possible also due to our new luminosity measurement, which has an uncertainty on the integrated luminosity of 0.7%. The LHC is a vector boson collider, as we just discussed. And of course, there has been evidence for vector boson scattering in all massive vector boson channels, and also with initial state gamma-gamma. In run 3, we have the first differential VBS cross-sections, as shown at on the left here. It turns out the LHC is also a lepton collider. We have actually a new measurement using, again, the full run 2 plus run 3 data with 446 inverse femtobarns, where we look at events that are perfectly PT balanced, so no activity outside really the final states, 2 protons intact that would then radiate 2 gammas, and these lepton pairs then scatter. And we see the evidence, the observation actually at 5.4 sigma for lepton-lepton and 4.0 sigma for muon-muon scattering. So Higgs is, of course, the important topic, and actually it is amazing to see how Run 2 has already been able to put us into the precision regime for Higgs physics. The Run 2 cross-sections consisting of about 1,000 data points in the standard template cross-section industry give us an uncertainty on the measurement of the order of 5%, where dominant uncertainty is actually the theory, as you see here. And also for the mass, we have made our final word for Run 1 and Run 2 with a combination of the data to obtain an uncertainty at the per mil level for the value of 125.07. One of the next targets, of course, apart from Higgs, which I'm going to show in a moment, is the question, what about charm? So we have measured all of these couplings to the third generation fermions, to the bosons, of course, and we started also with the second generation fermion-muons. For charm, we have made first attempts, and actually it's drawn here what our results are. These are the considered golden channels, and they give amazing results with Run 2 only when one goes to this multi-class classification using machine learning, where here you see, on the left you see the probability for a jet being B versus charm, so separating B and charm. Charm is here in blue, and on the x-axis is the separation between B or charm versus other final states. And we get to limits of the order of 5 times 10 to the, 5 times the standard model. In fact, our observed limit is a bit larger because you see that in one case we have an excess over the expectation. So this has been considered completely impossible. Even a few years back, we were discussing, is charm going to happen? Now with our improved tools, in particular the better flavor tagging, the much higher trigger efficiency, the further improved analysis techniques, and in the future also the new level 1 track trigger, we expect to make big improvements beyond just the square root of the luminosity, of course, and we hope to be able to get to evidence of charm couplings with the Higgs at the end of the high Lumi LHC. The Higgs production has been measured, of course, for Run 2. As Kerstin indicated already, we have actually a signal strength measurement at the level of 1 sigma consistent with the standard model, combining all of the data of Run 2 from Atlas and CMS combined. We have measured now with Run 3 the main significant channels, dihexo-4b, BB gamma gamma, and BBWW. These results were there before, and I'm just demonstrating here again, comparing run 2 and run 3, roughly the same luminosity gives us the same half of the luminosity of run 3 gives us the same sensitivity as in run 2. This is a new result using data up to 24 of the search for Dihiggs in the BB tau tau channel. This is a very difficult analysis using actually a large amount of Monte Carlo to describe the main backgrounds TT bar and Dre-Yan. You see here the DNN, the deep neural net outputs in different categories with different number of jets. And this is the combined result for the run 2 and the new run 3 data at 4 times the standard model, which is exactly the expectation actually for the case where the standard model would be correct. One of the things reported in the last 2 years was the excess at the TT bar threshold. 24 CMS observed this excess in the dilepton channel and found it consistent with the pseudoscalar toponium. We have now measured this in another independent channel, in the lepton plus jets channel, where different variables are used that are less sensitive to assumptions on the top quark mass and the jet energy scale. And so here in the lepton plus jets channel, the relative velocity of the leptonic top with respect to the hadronically decaying top is used. And again, we are seeing an excess of the order of 5 picobarns or so with relatively high significance, consistent with what we saw in the dilepton case. There are the numbers here from the dilepton CMS and ATLAS measurements and one of the NIQCD predictions. LHC is, CMS is also a flavor factory, and this is made possible now in run 3 using the Daimion trigger strategy. We have a very large sample of daimions with low PT thresholds, and that enables us to measure the time-dependent CP violation, both in the B0 to J psi k short and B sub S to J psi k short. You see here 1.4 million B0 and 16K B sub S candidates, and then using state-of-the-art flavor tagging, the asymmetry can be measured as a function of time and the direct CP violation, and the mixing-induced CP violation can be extracted, whereas here we are expecting a non-zero value, of course, and our data is on top of the other data with very competitive precision to LHCb and in agreement with the standard model. In the B sub S, actually, CMS provides the best measurement here with the red ellipse in agreement with expectations. We have also measured B sub S to mu mu in 6 different channels. B2S mu mu is, of course, a flavor-changing neutral current where new physics could actually appear in the loops here. And so we expect the branching ratios to be 10 to the minus 7. If they deviate, that would be a sign for possible new physics. And you see that our data is actually more precise than previous data in agreement and in slight tension, in particular in the B sub S to phi mu mu with the theory predictions, just as previous data from LHCb. Physics with heavy ions. I'm going very quickly. Of course, we are making the full range of measurements, hard probes, ultra-peripheral collisions, and also flow measurements. I would like to highlight the measurement of the system size dependence of charged particles using this nuclear modification factor, where we see in oxygen and neon a suppression of the yield as a function of PT that indicates energy loss. And this energy loss is apparently proportional to the nucleon radius shown here. We've also seen this expected from quark-gluon plasma, expected suppression of oxygen, and neon data for the epsilon 2s and 3s signals. Before I conclude, searches beyond the standard model, this is of course a very big field. I can only show you our summary plots and refer you to all the links on our webpage and therein. Just two examples of recent results. This is the monojets analysis with 22-23 data. It's really a precision analysis. It's a generic precision search because the most difficult background comes from Z2 new events, which have to be determined very precisely from other processes involving vector bosons. And from this one alone, we can actually set the Higgs to invisible branching ratio limit to less than 42%. That, of course, then to be combined with Higgs. And not least, search for muon detector showers, very long-lived particles where we have a new trigger in run 3 that allows us to search for particles with C tau as large as 100 meters. 30 seconds, CMS upgrade. We are bound to build the best possible detector for high-lung LHC. We want to have timing layers for the whole coverage of the cylinder, a silicon tracker up to eta 4 and a 5D high granularity calorimeter, and that goes with the trigger that actually does full reconstruction as much as possible already at the level 1 level. So this is going to be an event at the level 1 trigger, and this is to be compared with what we did today, which allowed us already to do the 1,500 plus papers that we did. The upgrade status is illustrated here. The construction is in full swing, and this brings me to the conclusion. Actually, my conclusion is invisible on this, so that saves time. Thank you.
Thank you, Andreas, for this wonderful talk and these amazing results from CMS. We now open for questions. Two questions there.
Hi, I'm interested in your WMAS data, so it looks promising. Do you have the anticipated uncertainty with the new data? And do you have a projection for when that might be completed?
So the first answer is yes, we made projections. We expect from that measurement alone an uncertainty of order 15 MeV. But one has to take into account that this is a completely different method, one that we haven't used. In our measurement so far, we have used just the PT of the lepton, not the reconstruction of the MT, of the transverse mass. And so the theoretical uncertainties that go into the PT lepton measurement are orthogonal basically to those that we are expecting here. So in the combination of the two measurements, we expect significant improvement still over the result that we have.
Thank you.
Okay, I take advantage. I got the microphone. So let me ask a question, so somewhat provocative. So then you have looked for physics beyond the standard model in multiple channels, right?
Yes.
Is there any anomaly that you want to point us to that we should look forward at run 3, that we should pay attention to make things more exciting and not just the standard presentation of, yeah, we saw limits and we saw everything, okay. But, you know, I discovered promptly a web page where you accumulate anomalies. Anything that you want to mention?
Thank you. Actually, we have been looking very closely from CMS in the diphoton final state around between 90 and 100 GeV. That's an area where we are going to look further with a certain urgency, of course, because there's an excess in the run-2 data. There's also in the low momentum final states in the context of electroweak kino searches, there are some deviations from expectation that we are trying to understand and where more data will be useful. These are the two things that stick out the most. There's a BSM working group at the LHC actually identifying also areas where both Atlas and CMS have excesses, and these are the two things that actually stick out. Sorry.
Okay. We still have time for one more question. There.
Thanks, Andreas, for the nice talk. You showed the threshold results for TT bar. Could you say something about how compatible the different channels are, and maybe also Atlas and CMS?
Yeah, this is a difficult question, of course. I mean, technically, they don't look very compatible if we take this at at the full scale. So even so, Atlas 13 and now the new measurement 5.3 seems to be discrepant. However, there are also different assumptions going in, different signal models. Curiously, the results depend not only on the TT bar handling, the background, the non-resonant background, but also the way we model the signal, which we have to understand more. And so, yes, this is input to more studies, and actually these studies in particular of modeling of the threshold are really taking off now.
Okay, I think our time is running out. Let's thank the speaker again.
Thank you.
Thank you.
And for our next talk, I have the pleasure to welcome David Quinelato, who will tell us about the ALICE experimental highlights.
Thank you. So I want to get rid of them.
Bom dia. Good morning, everyone. It's my distinct pleasure to be here today and show you some highlights from the ALICE collaboration. So let me first introduce you to the ALICE collaboration itself. We're nearly 2,000 members from all over the world, and our main intent is to understand matter in an extreme state. So ordinarily, we know that matter is confined into hadrons. Quarks and gluons cannot be found in isolation. But if you increase the temperature, or if you pack matter close enough, like what you expect to have at the core of neutron stars, you may reach a state which we know as the quark-gluon plasma, in which you no longer have color confinement, and you start having quark and gluon degrees of freedom. This is what we expect to create at the LHC when we collide lead-lead nuclei. So once we do that, we have a fair understanding of how the system evolves. We have an initial set of hard scatterings. Shortly after that, the system thermalizes, it reaches equilibrium. That's when we can talk about a quark-gluon plasma. And then it expands collectively, behaving like a fluid, which is this intermediate step here. Eventually, it cools down as it expands, and then it creates hadrons, which we eventually measure also at our detectors. If you measure a lot of hadrons coming out, or a lot of particles coming out, we even are able to tell that the impact parameter in these collisions was low. That's what we call a central collision. If you only measure a few particles coming out of your collision, that's a low multiplicity. That's a peripheral collision in which the impact parameter is relatively large. Now, the description of what happened in these interactions always goes via some sort of macroscopic perspective. So you have a statistical treatment, you have a hydrodynamic expansion, and that serves us pretty well in this system. This is in contrast to what we see when we collide proton-proton collisions. Ordinarily, in that regard, what we do is we model this via QCD-inspired approaches. That's when you have multi-parton interactions, but the key point here is that you follow each individual process. You really follow through microscopically. There are also intermediate systems which stand to teach us quite a lot, and I will say a few words about that: oxygen, oxygen, neon, neon, and as well as lead, lead. And in this broader context, there are a few key points that I want to focus on here today. First, one thing that we aim at doing is a precision characterization of the QGP. If we have a fluid, what are its properties? Further, at some point, you may wonder, what's the minimum set of conditions for me to reach a situation in which I can talk about a plasma? And eventually, everything cools down, hadronization kicks in, confinement kicks in. Can we see patterns? Do we understand how that changes eventually if you're dealing with these many collision systems? In order to answer this question and many others, we built the ALICE experiment at the LHC, and in fact, for the run 3 of the LHC, we have comprehensively upgraded our detector such that it was able to cope with with much larger interaction rates than in the past. And the key components that were upgraded were the time projection chamber, which now has continuous readout, so we can take up to 50 kilohertz lead-lead collisions. We have replaced the inner-mode tracking system, our ITS, with a system that's fully silicon-based. That's at the core of our detector. We now have a forward tracker, and we have completely overhauled the system with which we trigger and we determine centrality in our collisions. Now, all of this has enabled us to take unprecedentedly large data samples in run 3, which have been serving us very well. For the key system of lead-lead, we've managed to take 120 times the data samples that we took in run 1 and 2. And for PP, this number is even larger. We managed to actually inspect via software triggers around 1,000 times the size of the data samples that we've had in the past. And in addition, as I mentioned, we also have light ion collisions. I'll show you a few highlights. It's quite interesting from those systems as well. If we aim at understanding the quark-gluon plasma, a key point that we have to have is a reference that stands to represent elementary QCD, therefore having minimal high-density QCD effects. And for that, a key system is, of course, proton-proton collisions. We've been hard at work at quantifying what one gets in these systems, of course. I show you just two highlights in this slide. So the D0 meson, the prompt D0 meson cross-section all the way down to 0 PT, and here you see the B0 meson cross-section to 1 GeV at mid-rapidity. This is a first in this phase-space region, and it's really something that we're able to do because of the upgrade. So you really need the precision that you have in the tracking system, you need software triggering, you need a continuous readout to be able to do that. In both cases, you'll note that comparisons to theory look rather well, and it's even striking that we have experimental precision that's better than the model precision. Now, not content with measuring only D0 meson cross-sections, we also are able to understand how these relate with respect to the jets that come out of your interactions by looking at quantities such as jet angularities, which are per jet quantities that symbolize how momentum is arranged within each jet that we measure. Here you also have a parameter alpha, which determines if you're actually emphasizing collinear radiation or wide-angle radiation. And if you look at alpha equals 1, which is the result on the left, you'll see that the zero-tag jets have a peak which is closer to 0 than jets that are inclusive. Therefore, this points towards us having a jet. When you do have a D0 meson, that points us to having a jet in which momentum is more concentrated along the jet axis. Pythia does a fair job at describing this, so overall this looks like everything is fine, but it's not all roses if you look at PP. In fact, if you look at baryon production in PP, things already start to get a lot more challenging. I show you here the lambda C to D0 ratio as a function of PT, and in fact it's rather high. It's unexpectedly high if you compare to a standard approach such as Pythia Monash. In this case, you're basically dealing with standard QQ bar strings in Pythia. And in fact, in order to get this correct, or better, what you have to do is you have to resort to combinations of interactions between QQ bars that are called color junctions in Pythia, and then you get a much higher baryon to meson ratio. This is also, this need for some more complex modeling from the QCD perspective is also shown if you look at the Xi to pion and the omega to pion ratio as a function of multiplicity. In this case, this is known to rise already in PP, and what you need in order to get this kind of trend is not only a complex interaction between your partons inside a model such as Pythia, but you need this interaction to have a variable energy density, meaning your strings have to carry larger energy densities in order for you to break into more SS bar pairs. So it's not all immediate in PP. You already have what one could call many-body effects there. I'll come to that in a moment as well as I go towards hadronization at the end. Now, let me go to the limiting system in which we expect to have a QGP, which is the lead-lead system. And there we have this fluid-like expansion, which begs a few questions that I will try and focus on in the next few slides. For instance, if we have a fluid, you may wonder, what are the properties of this fluid? What are the viscosities? What temperatures do I reach? And eventually, if I have heavy flavor quarks that are embedded in the system, how do these evolve inside it? How do these diffuse? One way of actually looking at the diffusion of heavy flavor quarks is to measure the collective expansion of heavy flavor hadrons. Now, if you have a lead-lead collision, the interaction region in the transverse direction is actually almond-shaped because of the geometry of the colliding nuclei. This spatial anisotropy means that you have different pressure gradients in different directions, which in turn turns into a momentum anisotropy of the particles that you emit at the very end. We can quantify this anisotropy in particle emission in the transverse space by looking at the Fourier decomposition of the way that you emit particles, and the leading term of that Fourier decomposition is what we call V2, the elliptic flow. We have been measuring the elliptic flow for heavy flavor hadrons, including the prompt D0 family, as well as now the world first measurement of the lambda C plus baryon, which is now on archives. Again, this is one of those measurements for which we really needed to have the upgraded detector. The key point of having this measurement is exactly that it embodies how these charm quarks are interacting with your medium, and then eventually how you form hadrons. And you can describe what we see here by looking at models that include hydrodynamic expansion as well as protonic coalescence at the very end. Now, the fact that the medium expands gives you some other interesting phenomena. If you look at this geometry that you have in your system and things are expanding differently in different directions, you also have the formation of small vortices in your fluid. These vortices eventually propagate through, and some of the angular momentum that they carry may be imprinted on the hadrons that are emitted, and we can measure that promptly by looking at lambda polarization with respect to the beam axis in this case, which is the direction in which the vortices are rotating. We've done that as a function of centrality, so for central collisions all the way to peripheral collisions. For central collisions, if you think about the geometry, there shouldn't be any polarization. That's exactly what we measure. But as we go towards peripheral collisions, you start to have a non-zero polarization. What's especially interesting in this case is that because these vortices have to be created and then evolved through the system, because of this expansion, the intensity of the polarization that you measure at the end is actually rather sensitive to the bulk viscosity of your system. So this is something that stands to constrain how your fluid behaves rather well. Now, last but not least, I wanted to highlight also that we aim at measuring the temperature that we reach in the lead-lead collisions at the LHC. And in order to actually look at that, you can't just look at the hadrons that are produced afterwards because they only see the temperature at hadronization. But you can look at the dilepton mass spectrum, which should contain prompt thermal radiation. However, it's actually a very complex measurement because you also stand to have a lot of other signals. So for instance, LF vector mesons at low dilepton mass, or even quarkonia signals and at high dilepton mass. And even in the region in which we stand to have a larger chance of measuring the thermal radiation, you have a lot of heavy flavor background. Now, this is actually the state of the art. We are in the process of investigating the use of topological selections such that we can reduce the signal from heavy flavor and then really isolate how it looks like with the thermal radiation by looking at the slope of whichever remains here after we have successfully isolated and removed the heavy flavor background. Now I want to go to the intermediate systems, which are oxygen-oxygen and neon-neon, as well as P-lead. And here the question that is relevant is, what are the minimum conditions for me to be able to speak about a plasma? What does it mean that eventually I reach protonic degrees of freedom? And another relevant question is, if you do have a quark-gluon plasma, this medium is opaque to the passage of high momentum particles. Is it something that I would observe, for instance, in oxygen-oxygen collisions? So let me start by investigating collectivity. This is, again, the V2, so the elliptic flow that you observe in oxygen-oxygen collisions. Here you see the transverse profile of oxygen. You still have a geometry. It's over 10 times smaller, if you just think of the number of protons and neutrons, than a lead-lead collision. And we've been hard at work measuring the V2 coefficients for various particle species. You see pions, kaons, protons, phi, lambda, K0, all across the board. And you see that there's a lot of data, but there are some patterns here that I want to highlight which are very important. If you focus, for instance, only on protons and phi, these have approximately the same mass, and at low PT, they actually go together. They actually have the same V2. That's the region in which we have what we call hadronic mass ordering. However, if you go to intermediate PT, 3GV or so, and then beyond, you have baryons and mesons grouping together regardless of their mass. So the phi all of a sudden wants to go with the pion despite being much more massive, and the proton's all the way up there with the lambda. Why is that interesting? Because it points to the fact that what is actually determining the V2 that you're measuring is the number of quarks that constitute your baryons and mesons, which is again somewhat of a signal that you have a pertonic degree of freedom at play. Now, this observation has also been made in various other systems. In lead-lead, it's actually somewhat of a standard thing. We see also protons, lambdas going together here. But we've also seen it at high multiplicity p-lead as well as high multiplicity pp, which is a very interesting proposition because, in fact, this kind of phenomenon is something that usually in the modeling does require hydrodynamics and coalescence. If you ask Pythia, for instance, from the QCD modeling perspective, to get something like this, currently there's no way to do that. Now I want to cover, interesting, this is not showing up. I want to cover also the energy loss that you have of particles traveling through this dense medium that you may have created. And for that, we have the nuclear modification factor. I'm afraid that you're going to have to imagine a bit the equation that should be here. But the point is, this is the quantity that we call the RAA. And if the RAA basically compares the lead-lead particle production cross-section with an appropriately scaled PP cross-section. If the RAA is equal to unity, that means that the AA system is just a superposition of PP collisions. If not, it means that high momentum particles are suppressed. This is exactly what you see in the RAA of lead-lead. It's way below unity here. However, you do not see this if you calculate the same quantity for RP-lead. That's quite interesting. You did see protonic degrees of freedom there, but you didn't see any energy loss. This was one of the key motivations for the ROO measurement, which we did, and then lo and behold, you get an ROO that is actually below unity. However, there are actually many reasons for you to potentially have an ROO which is below unity. And one is maybe that you're not just dealing with the fact that you have this hot and dense medium, but you also have what we call cold nuclear matter effects. For instance, you have a nuclear PDF as opposed to a standard PDF when you collide protons, which is the reference that you're comparing to here. In order to isolate that, we have measured, okay, now the equation appears, that's interesting. We have measured also the RPO, and this actually includes the effect that you have of nuclear PDFs because you do have the oxygen nucleus in there. And we have calculated a new variable, which is the ROO divided by the RPO squared. That's what you can see on this plot here. And in this case, you see a suppression at the level of 4.9 sigma. The square here just symbolizes that you have two oxygen nuclei in the case of the ROO. So this is conclusive evidence that we have, in fact, observed protonic energy loss at the level of 4.9 sigma, which is not seen in P-lead and also not in PP if you do some wayside suppression variables that you can also calculate. Now, the RAA continues to be measured also for many other particle species. I want to show you just one example, which is the J-psi RAA. In this case, you typically have some other effects that are relevant. You have corconium suppression, in which CC bar pairs are suppressed by the medium. And you may also have corconium regeneration, which is something quite significant if you look at lead-lead. However, in oxygen-oxygen, this regeneration is expected to be rather small, and the ROO of J-psi is below unity, and it's also consistent with models in which you do have the presence of a QGP. Now, this was for the small systems. I want to now go back to the hadronization and to the hadronic phase that we have at the various collision systems that we're dealing with. Of course, confinement always takes hold at the very end after you have said everything about the protonic evolution, and we want to understand if this always happens in the same way in PP and in lead-lead. And I want to go back to the study of identified particle ratios. Here you see the lambda, psi, and omega ratios with respect to K0 as a function of multiplicity, and this is really a comprehensive set of measurements going from the very lowest multiplicity PP to the highest multiplicity lead-lead. And it's quite interesting that you see universal trends in these ratios, now including oxygen-oxygen, despite the fact that you have different initial geometries and so on and so forth. One aspect that I want to highlight here, which I find very interesting, is that if you look at the high multiplicity regime, you can describe this via statistical generalization models. That's the macroscopic point of view. In this case, what you would say is that you decrease the strangeness production in low multiplicity events because you have a restricted phase space to generate SS bar pairs. That's what's called canonical suppression. But if you look at how you model PP, meaning the small-scale view, this is actually possible to describe via modified hadronization in which you have density-dependent alterations of your hadronization mechanisms. So this is actually very interesting because it demonstrates that what we do stands to serve as crucial input to unify somehow these two views at the end of the day, meaning QGP signatures interpreted also potentially as many-body QCD phenomenology going at it from another angle. Now, because we have this rich hadronic phase, we can do quite some interesting things at the LHC as well. And I wanted to show you one example in which we have used this hadronic phase to characterize interactions between baryons and hyperons. On the left, you see the momentum correlation function between protons and sigma baryons. And here you see a correlation function between proton, proton, lambda. What's interesting here is that we stand to potentially measure the effects even of three-body interactions in our momentum correlation functions. This is interesting because if you think of multiple baryons interacting with each other, that's exactly what you expect to have at the core of neutron stars. So even though that regime is not easy to access, you can, at the LHC, take advantage of this dense hadronic phase to measure something, to learn about what happens at the neutron stars and potentially even constrain the equation of states that you have in that case. Now, I want to go towards the future and what that will bring for us. We have a comprehensive set of upgrades already for run 4. For one thing, we have the FOCAL, which is a forward calorimeter, which has both an electromagnetic and a hadronic component. This aims at studying gluon nuclear PFs down to a very low Bjarkin X, as well as doing some jet correlations with direct photons that are measured by the calorimeter. And we also have an upgrade in which we will replace the 3 innermost layers of our current silicon system with a curved, stitched wafer scale sensor which has barely no support structure. And with this, it will reduce the material budget by a factor of 3, and it will increase the tracking precision by a factor of 2. So that's quite interesting for a lot of the measurements, even that I was showing you here today. And this tends to also bring us to a level of precision with those that is much better even in run 4 already. Beyond that, for run 5, we have a big one coming, which is ALICE 3. In this case, what we aim at doing is to replace the main tracking system by one that is completely silicon-based, so we're able to cope with higher interaction rates, while preserving the state-of-the-art particle identification that has served ALICE so well to this day. The key point here is that we're going to have an unprecedentedly high vertexing precision, so we're dealing with, say, up to 3 micron precision, and there's a rich physics program that I have no chance of covering here today, of course, that we can do with that. So we have heavy flavor thermalization, even going towards Xi-CC, omega CC states, correlation between CC bar pairs, and even the possibility of measuring the QGP thermal emissions, but time differentially. The news that I want to highlight here is that, in fact, this was just approved in June by the CERN Research Board to go to the technical design report phase, the TDR phase, so this is quite an exciting time, a lot of work ahead, but also quite some potential. So with this, I'd like to summarize. We have just finished run 3, but in fact, we've just started leveraging what we did in run 3 in terms of the upgrades. You saw many results here, but in fact, there's way more if you look at the many contributions that we have in ALICE in this conference. And of course, the future is coming up. We have a comprehensive set of upgrades for run 4 and run 5 with ALICE 3. Thank you very much.
Thank you very much for this wonderful talk and exciting results. We have time for a couple of questions.
Thank you very much for your talk. One of the questions I just asked one. It's about your simulation for heavy ion collisions. You can simulate expected background, I would say, but since the models of quark-gluon plasma are not implemented in PTF, for example, how you can judge what kind of realization of the theory of nature is there if you observe some deviation from the background?
So I'm not sure, I couldn't get all the words there, but I think you asked about the modeling of lead-lead collisions in something like PFIA, was that it?
Okay, one more, I try to be quick. So you simulate the collisions in PTER,
Yes.
right? You simulate the background. When you observe some deviations from the expected background, how you judge what kind of signal or theory behind this? Well, you need to describe quark-gluon plasma, which is not implemented in PTER, right?
Right.
So how you can judge what theory, what signal behind that?
So the way this works, there's a long discussion to be had, so we can also discuss afterwards. But there's a quick view of this. Indeed, the usual way with which we model the QGP and LED is not actually PTER. So what we use PTER for is a baseline in which you do not have effects that are due to the presence of the QGP and no thermalization, because that's not there, right? So that is still a very, very valuable tool. And in fact, we very much welcome the possibility of understanding what we would have if you have a baseline with no QGP and then compare that to the other theories. Now, the other theories, they go about it a little differently. You have hydrodynamic phase, you have a set of components, software-wise, with which you can simulate this, and one of the challenges of the field is indeed to understand how to evolve from it, from this in a theoretical perspective. But of course, we try to focus on the experimental side, but we are aware that this is, let's say, one of the challenges.
So you're looking at the deviations, and then you will interpret these deviations kind of separately, not within PTER, right? Okay.
Yeah, that's one of the ways of proceeding, yes.
Okay, we have a question at the back.
So, yeah. So much of our understanding of the QGP properties, right, comes from a long chain of modeling from the initial to, the final state, et cetera. Can you identify one genuinely new property of QCD matter that we have learned from heavy ion collisions in the recent years that is actually robust against all of this long chain of modeling?
So that's a very interesting question.
This comes from a friend.
I know. Thank you. So I think that there are a few things which are interesting, which are somehow robust. For one thing, I think we can learn something about global polarization. If you look at that, you have the initial state, which has a certain polarization, not the one I was showing, but the one in which the system rotates. That actually survives the entire evolution. That, therefore, is a little more robust. We have a number of other things that could be taken as more robust than that, but I think that's maybe one example. I think we can discuss this maybe in the coffee break.
Yeah, so
we have time for one more question.
Yeah, could you go back to this, I think it's number 20, the slide 20, I believe it is. At least that's what
oops, sorry.
No.
Yeah.
What I have is, yeah, this one. I'm trying to understand the role of the three-body interaction.
You mean here? Yes.
Yeah, because if I look at the data, it seems that there's still quite a bit missing, and it's not clear to me that this has been an evidence the way you phrased it.
So my understanding here is the following. When you're dealing with correlations between these three baryons, you have two components. You, of course, still have the two-body interaction pairwise, and then you have a three-body component. And what we aim at doing, so the theory here that we have is one in which you predict the correlation based only on two-body interactions pairwise in this triplet. And then there's also another calculation in which you include a genuine three-body interaction. Now, I think what you're correctly alluding to is that the uncertainties here don't allow us to make an extremely strong statement. And in that regard, we aim at improving this by looking at more data. This is, if I remember properly, this is one subset of the data we have. And we aim at actually nailing this down with a better precision such that we can conclusively say that indeed we're sensitive to the difference between the magenta and the cyan curve here. So let's say this is work in progress in the sense that it will still improve as far as precision is concerned.
Thank you, and we have to go to the next talk, so let's thank David Kinelato again. And it's my pleasure to welcome for the next talk Patrick Rob, who will tell us about the LHCb experiment highlights.
Yeah, thank you very much. So indeed, I will present LHCb highlights and the new results that were presented during this very nice conference in Natal. So LHCb underwent a major upgrade before the start of Run 3. Thank you. With a new detector which was installed during LS3 of the LHC, where we increased the instantaneous luminosity where we run at by a factor of 5, up to 210 to 32 per centimeter square per second, and a pileup of about 5. So we replaced, in fact, almost all of the elements of the detector during this upgrade. You can see the fraction of elements which were replaced in red on the top side of the slide. Only the hardware of the calorimeters and of the muon system were not touched. And thanks to excellent data acquisition efficiency and very high data quality, we could increase significantly the statistics and the sizes of the data set that we recorded at the end of Run 3, which ended this year. You see on the right bottom side of the slide that we increased the statistics by almost a factor of 4 compared to what we had acquired until the end of Run 2. But not only we increased statistics, but also we improved the performances of the detector and of the real-time analysis, alignment, calibration, and the full offline data processing chain. So we could, in fact, improve much more beyond luminosity scaling over what we had during Run 1 and Run 2. So one very nice feature that we introduced during the upgrade of 1 of LHCb is this full software trigger, which is run in 2 steps. First one on GPUs, so 500 GPUs integrated in the event builder, which apply software reconstruction at the trigger level to reduce the data rate of the detector that we read out at the bunch crossing frequency, 30 megahertz, to output rate of about 100 kilobytes per second, which is then analyzed by a full detector reconstruction in CPUs with 3,800 CPUs, which run about 3,000 exclusive selection algorithms. We also implemented pioneering technique to save data that we record for offline analysis, saving only the interesting part of the events in a turbo format, which allowed us to save on disk 10 gigabytes per second to tape and 3 gigabytes per second to disk. So the successful design and operation of this system allowed to reduce costs and to provide high flexibility to optimize our software trigger when running conditions when changing at the LHC. And the performances detector followed, in fact, and were excellent. We observed that already during 2024, out of which these performance plots were obtained. You can see, for example, the primary vertex resolution with the new Velo detector, which is even better than what we had in Run 2, with resolutions up down to 10 micrometer in the transverse plane for the primary vertex. Long track reconstruction efficiency for the tracks traversing the full tracker, almost 100% efficiency as a function of pseudo-rapidity and momentum. Very good Chiron and Pion identification efficiencies that we got with the rich detectors, even with high multiplicity events. You see that we can reach very close to 100% Chiron identification for very low Pion misidentification. And then you can see also on the bottom side of the slide the effect of the online alignment of the tracking system that is visible on the upsilon masses constructed in the dimuon pairs, where you see the improvement of the mass resolution of the upsilon 1s, 2s, and 3s states before and after the alignment. So I said at the beginning that we also managed to record more events per inverse femtobar than what we had in Run 2, thanks to the trigger system, software trigger system that we implemented. You see, for example, the comparison of the trigger efficiency for multi-body B decay mode, so B to D pi and D into 3 bodies, where you see in black the efficiency that we had in run 2, and in red the much higher efficiency that we have now in run 3, thanks to the removal of the hardware trigger, in fact, and the trigger system that we have implemented. And you see also at the bottom of the slide the effect of the performances combined on the reconstruction of B to HH decays with the good momentum reconstruction, mass resolution, and PID performances that allow us to disentangle between all B to HH types, applying particle identification on the final state. Then a new measurement which was obtained with this run 3 data, which was presented at ICHEP, were measurement of the B0 and B plus lifetimes with very good precision. They were obtained with B to JEPSI K plus and K star 0 decays using 2024 data. And the precision that we obtain with these measurements of less than 1 per mil is very good compared to previous measurements. They are compatible with the world average and 3 times more precise compared to the measurement that we obtained in run 2 and run 1 with the LHC data. The lifetime ratio, which is also useful to compare with theory prediction, in this case that are shown here, are also very precise and better, more precise than the current world average. So lifetimes of B hadrons are very interesting and important ingredients for our physics program. And so the omega B lifetime was measured with more precision with run 2 data and presented also during the conference for the first time. So it's a measurement which is done relative to the Xi B minus baryon. So the omega B minus baryon is the baryon composed of 2 S quarks and 1 B quark, and the Xi B1 with 1 B quark, 1 S quark, and 1 light quark. And since the production fraction of omega B minus baryon is rather small, 2 decay modes were combined, omega B to JEPSI omega and omega B to omega C pi, to increase the statistics. And you see that here, rather precise measurements of the omega B lifetime relative to the Xi B1 was obtained. And this follows a series of several measurements of B baryon lifetimes presented in the past, so lambda B, Xi B0, and Xi B minus. All compared to heavy quark expansion predictions and compatible with them. So B baryons are a very important ingredient for the LHCb physics program because these are not produced in E plus E minus B factories at the upsilon-4s resonance. So it's something which is unique to hadron collisions at the LHC. And in particular, it's unique compared to B factories experiment in LHCb to be able to do B physics with these B baryons. So the Xi B0 to Xi 0 JEPSI decay and Psi2s was also presented for the first time at this conference. These are very challenging decay modes because they involve the reconstruction of the Xi 0 hyperend, which is reconstructed in purely neutral decays, Xi 0 to lambda pi 0 and pi 0 decaying to 2 photons. Since the pi 0 flight direction cannot be reconstructed in LHCb, this is quite challenging to reconstruct the Xi B0 with this final state. So constraints were applied to improve the mass resolutions of this state, but you see that clear signals of both Xi 0 JEPSI with the significance of 13 sigma and evidence of the Xi 0 Psi2s decay were presented this week, with the first measurement of the ratio of the 2 branching fractions as shown here of about 0.6. This opens the path, in fact, to the study of the rare decay Xi B to Xi mu plus mu minus, which has the same final state but without resonance in the final state, which is the equivalent of the B to G star mu mu, which is studied a lot in flavor physics, and studying it with B baryons will bring new insights on these decay modes. So a new hadron was also reported this week. So about 85 new hadrons have been discovered at the LHC since the start of the accelerator, and out of which 75 were found by LHCb. So a new state was observed using run 1 plus run 2 data, this BS star 5700, which decays into BS0 pi 0, also using pi 0 to gamma decays, with the BS reconstructed in DS pi, JEP psi-phi, and BS 3 pi decay mode. So the mass of this state, that you can see the mass distribution on the right side of the plot, is of 5,700 MeV, about, and 130 MeV below the quark model prediction for BS hadrons. It's also a narrow state, which is in fact quite surprising. There was a similar observation made in the charmed sector in Babar and Bell in 2003, with a DS star state decaying also in DS pi 0, which had a mass lower than predictions and narrow widths. There are still several possible interpretations for these states, which could be an exotic hadron molecule or effect of chiral doubling, mass splitting of the BS or DS states. Then, concerning the core physics program of LHCb, which is related to decays, rare decays, and TP evaluation of B hadrons, which will be described in more detail by Carla in her presentation tomorrow. There is one new result that I will mention, which is the measurement of the B to D star mu nu angular distribution. You know that B to D star mu nu decays are used to test lepton flavor universalities, comparing decays with a tau in the final state and decays with the muon in the final state with semi-leptonic B decays. And there is, at the moment, a 3 sigma tension between experimental measurements of RD star, RD, and the standard model predictions. And the measurement of angular analysis in these decay modes could help to test further new physics in this decay mode. So it's a measurement which is done with 5 observables, 3 angles, and 2 energies, which is quite complex and which was described in more detail by Tobias in his presentation 2 days ago. But from the angular distribution and energy distributions in this decay, you can measure for the first time directly Wilson coefficients, which are very sensitive to new physics in the D star mu nu decay, which are shown on these plots and compared with standard model prediction, and you see that they are in agreement between the two. Charm physics is also a very important part of the LHCb program, and a measurement of the Xi C0 to proton K decay and of its decay parameter was presented also this week, which was obtained with run 2 data in the decay using Xi C0 from Xi B decay in the decay chain Xi B to Xi 0 pi. So you see here the Xi B mass peak, which is used to measure the branching fraction of the Xi 0 to pk decay, which is quite small, 4.5 10 to the minus 5, and also used to measure the asymmetry parameter, so this alpha Xi C0 parameter, which is obtained from the angular distribution of the helicity angle of the Xi C baryon in the B decay, and the measure to be of 0.3. So this is something rather important because with polarization, you can access a lot of parameters, in particular for new physics searches in B decays, and having Xi C0 as polarimeter can be very useful for future measurements at the LHC and in the LHCb in particular. So LHCb also developed a physics program in other fields outside of B physics and charm physics, because of its unique geometral acceptance between detectors in the world. You can see here on the Birken X Q square plane the acceptance of LHCb, so which is distinct from the other experiments. So the W plus and W LHCt state fractions were measured with run2 data in the LHCb acceptance, so with the pseudo-rapidity of the muon in the range between 2.2 and 4.4, and shown on these two plots at the bottom, compared with the predictions from MC at NLO with good agreements. There was also a measurement of energy correlations with jets, which was presented in an area also different from the one of flavor physics that is used for LHCb. Usual for LHCb, you can see at the bottom measurement of this energy correlations as a function of the RL value for different PT of the jet, and the comparison with the PTM. In LHCb, we developed in the past years a quite rich ion and fixed target physics program, which was even extended thanks to the new capabilities of the Run3 detector during Run3. Because now with the new grade 1 detector, we can reach centralities down to 30% for lead-lead collisions, which was not the case with the previous detector. In addition, we have a unique fixed target system that we call SMOC2, which is a cell where we inject gas close to the vertex detector, so in the LHC vacuum, and with which we can provide collisions of the LHC beams with the gas at rest. And during Run3, in fact, thanks to the various combinations of gas we injected and the beams that were used at the LHC, we could take data in 28 different collision systems, which is much more than what we did in Run1 and Run2. And you see that also in this area, the capabilities of LHCb were really extended a lot. With lead-lead collision data, for example, we search for action-like particles, which could be observed in these collisions in ultra-peripheral collisions. And LHC, we showed a preliminary exclusion plot for these ALPS particle in the AIM-A and the coupling action photon coupling plane, excluding a new area below 5 GeV in this plane, which is complementary to other experiments. The main core of physics analysis that we do, in fact, in AV-ion data is the study of quark-anion suppression, because we have good capabilities for quark-anion reconstruction or AV flavor reconstruction in general. And I show here two recent examples of a study of upsilon 2s, 3s suppression in oxygen collisions compared to upsilon 3s, comparing upsilon 3s and upsilon 2s and upsilon 1s, and also measurement of psi2s to JPSI suppression in fixed target data that we collected with argon and dihydrogen, which provides a reference at the same center of mass energy, 113 GeV in this case, which is quite unique at the LHC. The last measurement that I want to show now, and that we presented also this week, is the measurement of prompt K-short and lambda, which was obtained using a small fraction of the Run2 data that we collected in special conditions in 2015, and which has used to measure precisely differential cross-sections of these states to be able to compare them with the generators and theoretical models. You can see examples of differential cross-sections on this slide, very precise measurements that are compared with various generators and models. Then, at the end of Run4, with which we will continue to use the current upgrade 1 detector with modification of the calorimeter in particular that we will do during the current shutdown. But basically, the same detector will be used until the end of Run4. Many observables in flavor physics will still be statistically dominated at the end of Run4. So there is a unique science case for flavor physics with some important measurements that can be done only at LHCb, continuing to do flavor physics at the LHC during run 5 and increasing significantly the statistics collected for flavor physics. And the full exploitation of the high luminosity LHC data, including flavor physics, is also a priority for CERN and for the European strategies. But the detector will suffer radiation damage at the end of run 4 and cannot use it beyond the end of run 4. So we have to build a new one that we call upgrade 2, where we will rebuild, in fact, all parts of the detectors and have a new one that will be able to run at higher luminosity up to 10 to the 34 per centimeter square per second, so meaning 30 interactions per second, and with which we want to collect 300 inverse femtometer of data at the end of run 5. There are many technical challenges that we'll need to overcome to run at this luminosity. In particular, we want to add precise timing of the order of 10 picosecond precision in the calorimeter or in the velo detector, in the reach, to be able to collect data in this very difficult environment. So the status of the project is we are now preparing technical design reports for the end of 2026, beginning of 2027, to give details of the technologies that we will use for this detector. So to conclude, at the end of run 3, we managed to collect a large data set of very high quality with the new detector that will allow us to obtain precision results. The first ones are starting to appear now, and many more will come soon. We are still exploiting the run 1 and run 2 data, which give us many diverse results. There were 15 new results presented in ICHEP, and some of them I presented today, and Carla will present other ones in her talk tomorrow. And we are preparing the technical design reports for the new upgrade 2 detector that we want to install for run 5. And you can see that we have many things to do in LHCb, but we have a very active collaboration, and a small fraction of it was present here in ICHEP, presenting more than 50 talks. So very active collaboration with a lot of young and brilliant colleagues. And for me, it was a real pleasure to have worked in LHCb for the last 25 years now. Thank you.
Thank you very much for this very nice overview of the many results. We have time for a couple of 2 questions maybe.
Okay, as you mentioned, RD remains as one of the most exciting topics in flavor physics. You mentioned a 3.8 sigma deviation, and you show several experimental results. I was wondering how much dependent on the original Babar measurement this tension is, and how consistent are all these results. I didn't understand very well. There seems to be several HCB measurements. I wonder how consistent are all between each other.
Yes, you mean on this plot?
Exactly, that plot.
So indeed, it is a combination of several measurements. There are some from Babar, Bell, LHCb and LHC experiments. So this will be described in much more detail by Carla, which will give all details the day after tomorrow. And so you will have answers to your questions.
I reserve it for Carla to
Yes.
answer my question.
Exactly.
Tomorrow, okay.
Tomorrow, yes.
Thank you.
In the heavy flavor summary talk.
Okay, we can take one more question if there is one. I can't see. Okay, if there's no more questions, we can thank Patrick Hobb again. And all the speakers. And we go for coffee break and we resume at 10:45 with the official opening ceremony.